right, when you think of the periodic table, what comes to mind? Probably high school chemistry, right? That giant, kind of intimidating chart on the classroom wall. But what if I told you it's not just a list? It's basically a treasure map. A map to everything in the entire universe, from the air we're breathing right now to the most distant stars. And today, we're going to crack that code.
So think about it. You've got 118 known elements. Is that just a jumbled mess of cosmic ingredients, or is there some kind of hidden logic, a secret code that ties it all together? Well, the answer is a big yes, and that's our mission today, to take what looks like chaos and make it crystal clear. So here's how we're going to do it. First, we'll get into the one big idea that makes the whole thing work. Then we'll learn how to actually read the grid, the rows and columns. After that, we'll dig into its hidden structure, find out how it can predict the future, basically, and finally bring it all back to today. Okay, first up, the big idea. You'll be amazed, really. The entire beautiful, complex structure of this table, it's all built on one single, surprisingly simple rule. And here it is. It's called the periodic law. And all it really says is this: if you arrange the elements by their atomic number, that's just the number of protons they have, their properties don't just change randomly, they repeat. There's a pattern. It's kind of like a musical scale, how the notes repeat, just in higher octaves. That repeating pattern, that periodicity, that's the key to everything.
All right, so with that one rule in mind, let's actually look at how the map is laid out. It really all comes down to understanding the grid, the rows, the columns, and the little families they form. So how do you read this thing? It's actually pretty straightforward. The horizontal rows, we call those periods. There are 7 of them. But the real magic, honestly, is in the vertical columns. Those are called groups. And you can think of them like chemical families. I mean, elements in the same group might look totally different, but they act in super similar ways. Kind of like siblings who have the same weird personality quirks. And if you take a walk across one of those rows, a period, from left to right, you see this amazing transformation happen. You start on the far left with super reactive metals. But as you move across, that metallic vibe starts to fade. By the time you get all the way to the right side, you're dealing with nonmetals. It's the smooth, totally predictable journey.
Okay, let's look at a great example. Compare 2 families from opposite ends of the street, basically. Group 1 and Group 18. In Group 1, you've got elements like lithium. They have just one single, lonely electron in their outer shell. This makes them, well, desperate to react with something, anything. But then you go all the way over to Group 18, with elements like neon. They have a completely full outer shell. They are the noble gases, they're stable, they're happy, they don't want to mingle. And it all comes down to those outer electrons. Okay, now let's zoom in even more. Because it's not just rows and columns. The whole table is split into 4 different neighborhoods. We call them blocks. And this hidden structure, this is the reason for the table's iconic and, let's be honest, kind of weird shape. So these blocks get their names from where an atom's outermost electrons are hanging out. You've got the S block and the P block on the sides. Then there's the D block, which is all those transition metals right in the middle. And the F block, that's where you find the real heavy hitters like uranium, is usually just tucked underneath so the whole table doesn't get ridiculously wide. The key thing is this shape isn't random. It's a literal map of how electrons fill up their energy levels. So why do we care about all this, all these blocks and groups? Well, this is where it gets really, really cool. Because all this organization, it gives the table an almost magical power. It can predict how elements are going to behave. So it's not just a list of stuff that exists, it's a tool for seeing into the future of chemistry. Just look at some of these trends. For example, as you go across a period, the atoms actually get smaller. Kind of weird, right? It's because the core gets stronger and pulls the electrons in tighter. And as you go down a group, they get bigger because you're adding more layers. But this isn't just fun trivia. The guy who first created the table, Dmitry Mendeleev, he saw gaps in his version and was so confident in the pattern that he predicted the properties of elements that hadn't even been discovered yet. And get this, years later, scientists found an element called gallium, and it was an almost perfect match for his prediction. How amazing is that? That is some serious predictive power. All right, so for our last section, let's bring it into the modern day, because the periodic table isn't just some dusty old poster anymore. It's alive, it's interactive, and it's something anyone can get their hands on.
As of right now, the map is complete, for now anyway. It organizes all 118 elements we know about, and that ranges from hydrogen, the lightest, most common thing in the entire universe, all the way down to oganesson, which is a super heavy element we made in a lab that only exists for a tiny fraction of a second. Every single one of them has its own special address on this cosmic map. And you know what's really incredible? All of this amazing, elegant logic, it's not locked away in some university library anymore. I'm serious, you could build your own periodic table, like right now. Just ask an AI to pull the data, pop it into a spreadsheet to arrange everything by atomic number, and then use a simple design tool to make it look cool. The fundamental code of the universe is literally at your fingertips. So when you boil it all down, the periodic table is so much more than just a chart. It's this beautiful, logical framework. It tells a story, the story of how atoms are built, and it gives us this incredibly powerful way to understand the building blocks of, well, everything. But I want to leave you with one last thought. This map, it organizes everything we know right now. But science, it never stops. So what happens when we find element 119? Where does it go? What new row does it start? And what new secrets about how the universe works will it reveal? The next chapter in this story, well, it's still waiting to be written.